Okay, so let's start the morning with dark matter at accelerator number 4 by Peter Harris. So please go ahead.
All right. So now we're to lecture 4. So this one, I started with talking about the dark sector in the end of last lecture. And so this lecture is going to be basically all about the dark sector. And we'll talk about how strange things can really get. And we'll talk about this actually, we'll start with low energy experiments, but then we'll also talk a little bit about the LHC and how this plays in the future, dark matter searches. So yeah. So out of, so just going from last lecture, right, we started to look at.
We can't hear you, so I don't know.
Okay. Is it better?
Let's keep going.
All right. So out of this, so out of these lectures, or out of last lecture, it kind of emerged the idea of looking for a low mass dark matter. And we started to look for like interesting signatures, right? So you get a lot of different signatures. You start to get displaced objects, right? And you get a lot of these light, like dark photons decaying to electrons and muons, mostly because they're light. And so this, in this lecture, we're going to keep going along this direction. And we'll also look at kind of where the community as a whole at accelerators is going. And so we'll talk a lot about future experiments. I'll talk about some of the like future analyses going on. And all of these are going to tie into the fact that we're going to take the dark sector and we're going to make it crazier. We're going to give it more dynamics, and it's going to give us more handles to actually look for dark matter. All right. So just as a reminder from yesterday, we started to add light dark matter, and kind of in its simplest form, we did it in the terms of a light dark photon. And the way we can get these light dark photons is through many different decays. So you can imagine making a lot of mesons and then looking for light dark photons in meson decays. You can look for light dark photons in kaon decays. You can look at them at an E plus E minus machine, right, in a monophoton analysis. You can look at them by scattering protons of a nuclei, having them Bremsstrahl along the dark photon, and you can also do it by electrons on the nuclei, having them Bremsstrahl. So going through, so I finished somewhere in the middle of talking about these different decays. So let me talk a little bit about experiments where you take an electron and you recoil it off a nuclei. And then what's going to happen is it's going to Bremsstrahl on a dark photon. This is, they call it dark Bremsstrahl on. And the idea here is to make a detector where you have electron comes in, it hits a beam, and then the electron moves, and you measure the electron energy, and then you look for nothing, right? So you look for an invisible signature. And so the idea would be you have an electron and nothing. It turns out the standard model doesn't have very many processes where you can get an electron and nothing. I think there's one. I'll show you the diagram in a few slides. And the idea then is to just measure the electron energy here, measure the electron energy here, and you can just take the change in the electron energy, and that's going to be the energy of your dark photon. Now, the thing about dark Bremsstrahl is that, well, in Bremsstrahl, when the photon is not massive, it's very likely that you have a basically infinite probability that your photon is going to have infinitely low energy. So in most cases, the electron kind of scatters and it doesn't move very much. Right? The scattering angle is very small. Question?
You say there's not. You see there's not many processes where you get an electron and nothing. What about like a W decay?
Yeah, so here, I'll show you the process. This is the process where you can get electron and nothing, right? So
You mean specifically for off the nucleus?
yeah, it has to be off the nucleus, right? So yeah, sorry. Yeah, so all right, so you can, so we get All right, so we look for electron nothing, and then the idea is to look for the change in the energy. And in the case of a normal bremsstrahlung, right, if this were a normal photon and not massive, this change in energy will be very small. But if it's a dark photon, you need to pull off a significant amount of energy because the dark photon has some mass, right? And so this change in energy becomes large. You can also improve your detector and do what's called, instead of a missing energy surge, a missing momentum surge. And so the idea here is to have an electron on a target, and then you measure the electron momentum, and you actually try to measure the transverse momentum, which is the momentum of the electron off of the beam axis. So the idea is that the electron will scatter and it will start having some vertical momentum in this case, right? And you then measure this by making a magnetic field that goes into the board here. And so you look for momentum measurement of the electron. And then of course you measure the electron. So now you get a full 4 vector for this electron. But it turns out actually the transverse momentum is the most powerful variable. And so you can make an observable where you just look at the electron's initial transverse momentum, which is hopefully something like 0. And then you look at the electron its final transverse momentum, and this is going to be equal to your dark photon transverse momentum. And it turns out when the dark photon is heavy, it can give the electron a much larger kick than if things are light, right? If it's just a photon. And here's actually what they look like. So the left here is the missing energy. So your background in this case is just going to be an electron scattering off a nuclei, radiating a photon. And so here, this is the electron energy after it scatters for a 4 GeV beam. So the initial electron energy is going to be 4 GeV. And so for your background, you see that most of the final electron energies are close to 4 GeV. But then when you add a dark photon, the final electron energy is not 4 GeV anymore, it's 1 GeV. And so all of these different colors are different dark photons, different dark photon masses. And you can see basically all of them, once you add a mass, right, all of them suddenly have take out a lot of energy of the electron. The cross section for this is like this. Effectively, you add this mass term. So I won't walk through that, but suffice it to say, once you add the mass term, the dark photon takes a lot of energy away. Yeah.
In terms of measuring PT versus missing ET or missing both, I guess, is there a difference in the detectors themselves? I think you said something about a magnet.
Yeah. So this guy, you need to measure this electron momentum, right? And in order to do that, you need a magnet, and you need like tracking chambers here. So you need to measure the charged particle track before you have it decay in like a calorimeter. In the missing energy, you just have a calorimeter. So it's basically like, if you want to just do a missing energy surge, you can just do a calorimeter. And let's say you want to upgrade your detector, right? You just put a tracker in.
Okay, so it's direction plus energy deposited versus just energy deposited?
That's right. So it's just adding this directional information gives you this new observable. And all right, so this is a missing energy surge where you have this background. Once you have transverse momentum, you actually can get rid of this background. And the reason is that you can once you have tracking, you can actually identify photons and separate them from electrons, right? And in this instance, right, basically bremsstrahlung photons are a background, but you can remove them because you now have photon ID. And so this is what you get for the transverse momentum. And so this is the x-axis here is the electron transverse momentum. The background is in this first bin. It's this black thing. So you basically, the amount of transverse momentum that electron usually has is tiny, right? You can barely see it. Some people call this a backgroundless surge. And then basically, if you see the electron has any transverse momentum whatsoever, it's indicative of a dark photon. So, and the heavier the dark photon, the more the transverse momentum. So there's 2 experiments. The reason I present both of these is because there's 2 experiments now looking for dark photons that decay invisibly. There's the Na64 experiment. And the idea here is this is at CERN, so you have an electron beam that goes in on a target, and then you measure the decay components from your target. So you actually have a magnet afterwards to measure, I guess it measures the electron momentum. And then you have various detectors. You have a electromagnetic calorimeter, hadronic calorimeter, so you can measure many decays. So the strategy here is that, well, this process where electron radiates a dark photon and decays invisibly is a clean signature. Most of the time, the electron will radiate and give you like crap. So you're going to get all sorts of hadronic like stuff in your detector, and you want to veto those events. So you get, yeah, like hadronic crap, which is just pions and kaons. It's a mess. So the idea here is you have these detectors to veto those decays, and then you just look for this signature where you have just an electron and missing energy and nothing else. So the other experiment that is doing this is called LDMX. So this is an experiment that's being constructed at SLAC. It's in the design stage, but it's approved. And so people are very actively working on this thing. And the idea here is to have a magnetic field, tracking chambers, and then have calorimeters so that you can veto all the other decays. And so you fire your electron beam in here. And then instead of at CERN, it's a 100 GeV, at Na64, it's a 100 GeV electron beam. Here it's a 4 GeV electron beam. So this changes your dynamics a little bit. Yeah.
Is that detector being built specifically to measure this one process or direct?
Yes.
Okay, cool.
Yeah. So they are measuring some other like nucleon processes. So you can do some nuclear physics with it. But the main reason is to search for dark matter. And so the idea here is that you fire your electron in, and then you have your target is here. Target's here. So you fire your electron in, you measure the momentum before it hits the target, you measure the momentum after it hits the target, and then you get the calorimeters to get the images. And this is, if you're interested in new projects, this is building up. It's very active right now. People are very excited. Yeah, here's a perhaps much nicer diagram of it, where you have the electron coming in, scatters off, and then you look for an invisible signature. And all of these calorimeters are to make sure this is really invisible. So again, right, this is basically this is like our monophoton analysis or monojet analysis, except now there's no monojet or photon. It's just a scatter off a nuclei, and it's just invisible. So it's I guess it's a mono-electron analysis, but same idea. The other thing to mention about these experiments is the way to do this effectively is a single electron at a time. So it's very easy to make a beam of a gazillion electrons. So you can have 100 electrons come in and hit your target and all scatter. The problem is 99% of the time, the electron's going to radiate pions, etc., and kaons and so on. And so if you have 100 electrons going in at a time, you will have a busy event, and you won't be able to necessarily separate out all the 100 collisions. So you actually have to configure your beam in a special configuration where you go one electron at a time, or a few electrons at a time. They're studying one electron at a time now, but they're going to look. They're trying to see if they can do a few at a time. I'm trying to convince them. So. Yeah, all my friends are on LDMX, and every time I argue with them about this. But yeah, so the idea is you can do one electron at a time, and then you just radiate something invisible, and then you have a clean signature. But you have to configure the beam this way, which is very annoying. So here are the bounds. So the left is Na64, the right is LDMX, and to kind of the x-axis here is this y variable. So epsilon squared times alpha dark times the mass of the chi over the mass of the dark photon to the fourth. Yeah, question?
I have a question regarding the single electron B.
Yeah,
So instead of having it on target, can it be like T2K? Because T2K have an off axis detector to select for, like you lose flux, but you have a cleaner event.
no, so the issue is that most of these interactions, there's going to be stuff here. So you need to, and it's going to be along the beam axis, right? So you can't, like T2K, right? You just measure the off axis
Yeah.
like object, but you need here to veto. So most of the time, you're going to get the electron will scatter, right? And then you're going to have something else like, so this will hit the nuclei. And then you're going to, this nuclei can break apart, right? You can get pions and kaons, right? So this whole thing will break apart.
Oh, okay. So
So-
it's not. Oh,
Yeah, so you can imagine there's a quark here, and then you produce mesons, right?
right.
So, and the idea is that you want to veto this, right? So, you want to veto that activity and just look for the case where you just have an electron and like nothing, right? So,
Okay. So if you can't have an off-axis detector, because you want to, if you don't just want to veto that, but you also do not want to miss out on your dark matter.
yeah,
Okay.
I mean, the other things you want to veto, right, are like Bremsstrahlung, right, where you have a photon. So that's another case. And again, right, this will go through your detector. So
Okay.
this is probably, I'm just thinking, this is the dominant process, but you also have
Right.
analysis, got it.
Okay. Cool. Thanks.
Okay. So here's the sensitivity. Yeah, and these are actually for the same couplings. So here's this y variable, which is a proxy for the coupling. And so you can see this is the Na64 projected bound. So the idea is that we want to get go below these relic lines. This is the minimum coupling that would allow you to not overproduce dark matter. And so the strategy is to get below. So Na64 will, with this many electrons on target. Na64, you can actually replace the beam. You don't need to fire electrons in. You can fire muons in. And then this is actually the result if you fire muons in and electrons. So you can actually get more sensitive. And here's the LDMX results. So here your same relic lines as here. And the result with the first phase of running is this blue line. So you can cover the relics here. And then if you add, I think it's another factor of 10 of data, you can come like very well cover like these regions. So you can probe down to really small couplings. These experiments are ongoing. Na64 is up and running. So you should get excited when you hear results from these. So yeah, I mentioned Na64, you can fire muon beam. There are other experiments that are looking at this as well. So there's an experiment called M-cubed. So muon missing momentum. And the idea with muon missing momentum is basically to do the same idea as LDMX. So, but with a muon beam. So you need to find a muon beam, then measure the muon momentum. You have a target. And then you measure the muon scatter afterwards, and you get missing energy. Now, what's the point of muons? Well, so it's the same idea as the electrons, except muons are heavier, so you can actually probe different models. In particular, you can probe scalar models, right, where you can take advantage of the power coupling that's much larger for muons. You can also probe models where maybe your dark photon just couples to muons, and maybe that model explains G-2. But you can also actually just probe the standard dark photon. So if you just actually do some projections with a muon beam, and there's potentially a muon beam at Fermilab we can talk about, but you can actually get bounds. So the muon beam is a bit higher energy than this electron beam. So you can actually get bounds that are comparable to the bounds from LDMX, but at higher masses. Question?
So I'm not clear, I mean, if I want to look at some kind of scalar dark matter, why would the heavier muon help me out with that? I mean, it's not a Higgs, right?
No, but it still has a Yukawa coupling. So
Right, but if my mass doesn't come from this other scalar, then I wouldn't expect my Yukawa to this scalar to be greater, would it?
no, see, we always assume that the coupling is proportional to the mass of the particle. Oh, so I understand the point, right? So it's not giving the particle mass, but we assume the coupling is Yukawa. So what it could be, so typically one way to do this is that this scalar mixes with the Higgs. Right? That's typically the way you assume. And then it has, by construction, has a Yukawa coupling. It's the same. So usually we embed this in like a singlet model, like the one I showed 2 lectures ago. And then it has a Yukawa coupling. So that's, and then you get the enhancement. So you have a muon here, muon, and then the coupling is scalar to the muon, right, is Yukawa.
I see. So I guess I could have some scalar though, where I couldn't have mixing with the Higgs, and then all bets are off.
Yeah, all bets are off, but basically at that point, so at that point you start playing, you have either a spin 1 particle where you just kind of vary the coupling however you want, but you assume it's uniform between the particles. And then the scalar is kind of a counter to that, where it's not uniform. And yeah, it doesn't need to be the mass of the muon, proportional to the mass of the muon, but we just do that because it makes it easier for presentation and motivation.
Sure.
But I mean, these days there are models where you can vary the couplings to all of the leptons, right? And sometimes they call them scalar models, sometimes they call them like spin or dark photon models, but it kind of depends on the grander properties of the model.
Makes sense. Thank you.
I mean, and the spin, right? Yeah, go ahead.
Thanks. Could you say a little bit more about how this could resolve the G-2 result?
Yeah, so maybe I won't do too much because I was thinking this would be a good discussion topic for tomorrow.
Okay, great, sounds good.
But you should think about it for tomorrow. Okay, so yeah, so here's the M cubed. And yeah, you can ask me more because I'm trying to see if we can get this built. And the one thing I will say about G-2 is here's a plot, and here's the G-2 coupling that you would expect. It's up here. And here's the M cubed bounds from various styles of running. And suffice it to say, you can probe it. Interesting stuff.
What was M cubed? Sorry.
What does it stand for?
Yeah.
Muon missing momentum.
Got it. Okay.
So the other thing you can do is you can start looking for dark objects decaying from mesons. So here's one that I think a lot of people like is kaon decays, decaying to a pion or a pi naught, and then radiating off a dark axion, radiating off an alp. So you can have your axion-like particle decay off the kaon. There are actually a few ways you can have kaons decay to other things as well. But the idea here is to look for a kaon that decays to a pion, right? Either a charged or neutral, and something invisible. And there are a few standard model cases where you can have this. You can have a kaon decay to, if it's a charged kaon, you can have it decay to pion neutrinos, and you can have neutral kaon decay to pi naught in neutrinos. And so there's actually 2 experiments that probe this. So the NE62, which is at CERN, which has these CERN names are very confusing. I always swap. So I just showed you NE64, right? This is NE62. And I might mix them up again. But they're very different experiments. Babette is on NE62, so you can ask her about this. So the kaon decays to pion neutrinos, and that's what NE62 measures. The kaon decay to a pi naught is measured by this experiment Koto, which is at Japan. And then they want to build a bigger version of NE62. And now they have a clever name for it. call it clever. I like to call this cleaver, but but yeah, I think it's pronounced clever. That's the how they pronounce it. I'm not on that experiment, but you can ask about that. So this is the Koto experiment. So the idea here is to look for a kaon that decays to pion and nothing, pi naught. Pi naught decays to 2 photons. So you have your kaon beam that goes in to this detector. You measure the momentum earlier. Well, you know it from the beam conditions. And so you know the momentum of the kaon, it comes in. And then you have a bunch of things to veto other particles coming into the beam. And then the kaon will eventually decay. It's a long-lived particle and will decay to 2 photons. And so you measure the momentum of, or the energy of these 2 photons. You reconstruct the vertex, and then you can actually see if there's some missing energy here. Right, so that's the idea of the Koto detector. They have an interesting deviation from the standard model for this process. So I encourage you to read their paper if you want to get excited about this. If you want to ask people, if you want to ask your friends about, you can ask me about my opinion of this deviation after this talk. But it's a real deviation at the moment. So to check this deviation, this is the Na62 experiment, which is trying to look at the pion decay process. And here you have your kaon beam coming in. You measure the kaon properties here, right, with this tracking detector. Then the kaon eventually decays, and you get a pion, and then you reconstruct your pion with some tracking detectors here, a rich detector. So you can ask me about this at some point. And that does the pion identification, and then you have some calorimeters. And just to give you an idea of the scale of these things, so kaons have a long lifetime. So this whole experiment is actually 270 meters long. So this like giant hallway. It's a long beam. It's kind of fun to go see it if you're at CERN. And I mean, same here, actually, there's a long beam before it gets to the Koto experiment. Koto's not as big. Okay, so these are the 2 experiments. Yeah.
Sorry, so with this neutral kaon decay here, I guess the only signature we have is these 2 gamma rays.
Yeah.
So how are we using this process to constrain this process where there's a out coming out instead of the neutrinos?
Yeah, so the way you do that is you measure this process, the rate you measure the rate of kaon decay to invisible and pi naught. And you check to see if there's a deviation from your standard model prediction. So you end up making a plot actually like this. So the plot is this is the cross or the branching ratio of a kaon decaying to a charged pion, and the branching ratio of a kaon decaying to a neutral pion on the y-axis. And so you measure this cross section or this branching ratio, and so you'll get some number, right? So at the moment, Koto sees, I think there's an excess of events, so it's like up here. It's quite far from the prediction. And so you then have like a bound for this. And then the idea is that if it deviates from your standard model prediction, it's some indication that something's off, right? And the nice thing is, since you have both kaon decays, you can measure both kaon branching ratios and make a plot where you have the like Koto measurement on the y-axis, the Na62 axis on the x-axis, and then you have like a spot where you get your measurement, and then you can measure the deviation from the standard model like observation or prediction. And so that deviation will tell you that there's some anomalous decay. Whether this is dark matter or not is something that you can't figure out just from this experiment.
And so for the neutral plane, that was that dactyl term is your tag for this decay?
That's right. That's right. The way you actually look for the invisible part is a missing mass. So you reconstruct the photons, and you have the whole system is constrained. So you know the momentum of the kaon, you know the momentum of the photons, so you can make a missing mass squared variable. Yeah.
So my question was, so I see those green bands, or maybe I should ask you actually after that, why are they like such diagonally positioned?
Yeah, so that's a good question.
I mean, we can, it's
Yeah.
not so relevant, but we can discuss it maybe in the break. If,
Yeah, I mean,
somebody-
I think Yuri might know the answer to this. I don't off the top of my head. So,
Okay, no problem.
but yeah, we can talk about this later. Yeah, I mean, MFV, right, is for some minimal flavor violation. So it's some flavor violating model, but so if it's flavor violating, I guess you can imagine that the pi naught decay will be different than the pi plus decay. So you can have some deviation of one of them and not the other. But I think that's my very hand wavy explanation, right? Yeah, so these are the can decay experiments. Yeah, I'll keep going, but this is actually the NE62 came out very recently with a new result, and they actually start to see the standard model process of cans decaying to pi pluses and or charged cans decaying to pi's and neutrinos. And so you can see a few events already, and they're actually putting very strong bounds with it. So in fact, it's a kind of an exciting time for NE62. They're going to make kind of a very definitive statement about this branching ratio very soon. I mean, that result is from this year. So, all right. So now you can imagine even more crazier decays. So you can imagine ETAs decaying to a dark photon. This is a strange dark photon model that will give you a pi naught photon. You can imagine it decaying to kind of a conventional dark photon. These are proposed experiments that use ETA beams. So it turns out you can make an ETA beam by firing a proton on deuterium. And then you can get ETAs and ETA primes on helium-3. And suffice it to say that this is another type of decay that can probe for these dark matter. And you can look at this in our epsilon dark photon mass plane, and you see you're quite sensitive. So, I'll just leave it at that. Yeah.
I can talk loud. So in these models where these mesons are decaying into some kind of dark sector particle, is there something specific about the model that's requiring that specific meson?
No, so this is, I mean, so you can play around with the model, but this model on the right is just your conventional dark photon. It has normal, like equal coupling or some coupling that's uniform for all the quarks and a coupling for the leptons, right? It's kind of the conventional prescription. You can play around with the couplings, right? So you can, for example, turn off the lepton couplings, which is what's done in this model. And for these ETA decays, you still have the kind of same final sensitivity. It's similar, but it doesn't really change things out. It depends really on the decay, the process, but basically they're all kind of common models will give you will result in some modified decay of your mesons.
So are there like kind of unique higher cross sections for the meson decays? I guess what I'm trying to imagine is why build these kind of seemingly fine-tuned detectors.
So well, it's not seemingly fine-tuned, but so the reason we build them is because we can, right? It turns out that you can build these like a very high intensity ETA beam. But I mean, to that point, actually, the reason I put this plot in here is that this is like a baryonic dark photon model, where it would in ETA decays, you would be very like have enhanced sensitivity over like some of the other searches, like in KN decays. I mean, in KN decays, right? The model people like to point to is not the dark photon; it's an ALP, right? This is usually the one that gives you. It's usually the target in this case, because you're actually sensitive to this ALP gluon coupling.
Okay, interesting. Thank you.
So yeah, it's. I mean, I'm kind of. There's a lot of phenomenology in the background, and I'm kind of gliding over it. But each different experiment has like a target Lagrangian that they're looking for. That's usually the benchmark. Yeah. And I tried to pick the kind of money plot for each of them. So here's another one, or another experiment. This one uses a low energy muon beam. And the idea is to look for this process where you have a muon radiates a W that then decays to an electron that then radiates a dark photon. So it's a crazy process, and you get 2 neutrinos out of it, and you get 3 electrons in the final state. And the reason we can look for this is we can build a super intense muon beam. So you build a super intense muon beam, and then you fire it at a target. And this muon beam is very low energy, so you can kind of put instrumentation all around it. So you fire this super intense muon beam, you hit the target, and then you just look for 3 electrons. Right, so 1, 2, 3. This is all in a magnetic field. It's very small, right? This is 10 centimeters, right? And right, it's actually this image is larger than the experiment, right? This is larger than 10 centimeters. So this is another one, that takes advantage of the fact that you can make a very high energy muon beam and run it. This is actually being run not so far from here at PSI. So it's like a 2-hour drive, I think. It's maybe an hour and a half if we take the tunnels. So you can also get bounds on dark photon. So they use the conventional dark photon model. And then you can make plots here on your dark photon mass, mediator mass, and your coupling squared bound. And you get these bounds here right in the kind of elbow or armpit of the constraints that we already have. So
I guess the standard model photon is your background.
yeah, so in this case, we're just looking for standard model photon. So the idea is you get the mass of these electrons, they should be close to 0. And yeah, you do a fit, right? Extrapolate. This also is like there are other processes where you have a muon to electrons that they're looking for. So it's not just dark photons, but
What was one of those processes?
so like lepton flavor violet. Which I'll talk about potentially a model that will give you that later. All right, so the question came up yesterday, and I wanted to talk about this, is that there's also these millicharged particles. So what are millicharged particles? Well, the idea is to have a dark photon, but make it massless. And so now you have a dark photon field and a photon field, and these guys can kinetically mix. So you can give it some mixing term that's small, 10 to the minus 3, 10 to the minus 2. And then you can write down your fields. So you have a dark photon field, then you have a mixing term. And then you can rewrite this. Oh, and you need to give this model some dark matter to explain it. So if you write the full Lagrangian, you have a dark sector particle. So you have a dark matter chi. This is a dark fermion, and it interacts with your photon, with your dark photon. Yeah.
Sorry, so when we have a massless dark photon, I'm not sure why we distinguish between the milli charged case and the other basis change where I redefine my photon. You know what I'm talking about?
Oh, why can't it be massive?
No, but if it's massless, there's usually these two, they usually call it, we have these milli charged particles, but
Yeah.
and that's when I redefine my dark photon to be some V plus A with my photon.
Yeah.
But I have this other choice where I can redefine my photon, right?
Yeah.
And then I don't get milli charged particles. So why do we make this distinction when I have a massless dark photon? Because I can make either choice, if that makes sense.
Yeah, so you don't have millicharged particles, but you have charged, standard model particles have
Correct.
millicharged in the dark sector.
Right.
Yeah, so I don't know how to measure standard model particles that are millicharged in the dark sector. But if you can come up with a way to do that, it would be a very nice paper.
But I mean,
Yeah.
there would.
I mean, answer this. So it doesn't matter, no, it's just the basic
Yeah.
definition. But in massless case, it's clearly that one linear combination couples to us and the other doesn't. So that's the easiest way to keep track of things. It's like you don't need to use canonically normalized fields, but everybody does it. It's easy. And in these two extreme cases, when one guy is much heavier than the energies that you're probing, the dark photon, it just makes more sense to use the dark photon. If the other where the dark photon is much lighter or massless, then it's much better to charge the midi charge version. You don't have to do it. But it's convenience. Okay, fine. Yeah.
All right. Okay, so all right, here's your dark sector particle, right? And it's interacting with the dark photon. And you can do the usual trick and parameterize it so that you get a charge for your dark sector. So the idea here is that your dark photon now is mixing with the photon. And so that means your dark sector particle will now have an interaction term with the regular photon, right? So you'll get a modified term where the dark sector interacts with the photon. And what this means is that your charge, you end up with a modified charge. Let's say your dark sector charge had a charge of an electron, a dark electron. It's the same, can say it's of the same order of the normal electron charge. But now you'll get a very weakly charged particle because its charge will be suppressed by the mixing factor. So you end up with a dark photon field, but also with millicharged particles. And so how do we search for millicharged particles? So here we have there are various detectors to do this, and actually there's various other constraints. So here's the kind of the exclusion plot for millicharged particles. So this is scanning the mass of a dark fermion all the way from 1 electron volts to 10 to the 14. And here's scanning the charge. This is epsilon, which is the kind of mixing parameter for your charge. And you can see basically there's all sorts of constraints. There's constraints from the sun, right? Because you'll have solar production. Millicharged particles will affect solar production. There's constraints from supernova, BBN, the number of effective neutrinos in the CMB. But it turns out that in the LHC beam dump experiment region, there are no constraints, or they're very little. And these are things that you can constrain because you can produce dark sector particles at the GeV range at the LHC or at a beam dump just through normal Jolien processes, where now you have them decay to dark photons, right? Because they have this photon coupling. So you can produce these guys, and there's an experiment that has done this recently called this Millikan experiment. And the idea is to have scintillator that's heavily doped, so you can measure charged like very weakly charged particles going through it. So you look for, and you look at those produced at the LHC. Okay, so I won't go into too much details beyond that, but suffice it to say they actually have first bounds. This is not a big experiment, right? This is right. This whole thing is 3 meters by 1 meter by 1 meter, so you can stand next to it. And this is actually there's like a service area near CMS. So it's in like one of the tunnels near the experiment. So the idea is that once you put it in a tunnel, it's far enough away from the collisions that all the other particles are going to disappear, and you're just going to get millicharged particles. Okay, yeah. Now there are plans to make even more millicharged particles searches. So here's a list of bounds. So, and again, this is now scanning a much smaller range, right? So going from 10 MeV for millicharged particles to 10 GeV. And you can see these are potential future bounds of various experiments, right? So, and actually it turns out that neutrino experiments like Dune are going to be the most sensitive for these. Okay. All right, so that's another model. So now I want to talk about what some people like to call the lifetime frontier. So this is another relation. And just to kind of preface this, just taking one of the previous plots, just as a reminder, we're going to very small coupling values. And these small couplings means that things can be long-lived, right? So when the couplings get very small, your dark photon can be long-lived, but it also kind of is a, once you go to long-lived, once you start looking for long-lived particles, it turns out it's a great way to probe very small couplings. And it's also nice because there's not so much background, right, that's long-lived. And so, well, what are some other weakly interacting particles that, are similar to dark matter, that have weak couplings? Well, neutrinos are. So we can imagine taking neutrino experiments and repurposing them to search for dark matter. And so in a typical neutrino experiment, you produce neutrinos. It's a typical beam-based neutrino experiment. You produce neutrinos by firing protons on a target, and then producing a lot of mesons and letting them decay. So this is not so different than what I showed you earlier, where we produce mesons and try to have them decay to dark photons. But in this case, with neutrinos, you have them decay to some neutrino. Then your neutrinos can do something fun, like oscillate. And then you try to detect your neutrino, right, in a big detector. So in a nice large volume detector. And so you can imagine in the case of looking for dark matter, you can have the same scheme. You can have the scheme where you fire a proton on a target, it produces your dark matter. Now the dark matter may or may not do something interesting, right? And then the dark matter, again, is very weakly interacting. But if you have a large enough volume detector, you can measure dark matter scatter in your detector. And so this is actually, turns out, very useful. And people have been going around repurposing neutrino detectors to search for dark matter. And the idea, kind of the way to think about it in this scheme is that we have a beam that makes dark matter. And then we basically take our neutrino detectors and we turn them into direct detection detectors, right? And we look for dark matter direct detection. Yeah.
What's the material in the detector? What's it scattering off of?
It could be whatever you use your neutrino detector for. So I'm going to show you bounds of mini boon, which is liquid argon. You can imagine, using T2K for this. You can imagine just pick a big neutrino detector that has a beam fired at it and use it.
Okay, cool. Thanks.
Is the gain here just the high momentum of the chi over direct detection?
Oh yeah, so yeah, the gain is the high momentum, but it's also the fact that you're making a beam, right? Like direct detection, right, is just dark matter in the universe, right? So you could imagine like making a beam and then trying to fire it at like a direct detection experiment, right? I think people are thinking about this. I'm not sure. I can't think of an experiment off the top of my head. But yeah, you can imagine doing that. So here's a mini boon experiment. So the mini boon is designed to look for short baseline oscillations, right, of electron neutrinos. And so the idea with mini boon, the nice thing though is that you have a nice big proton beam, you produce mesons, and so then in this case we can imagine our meson decays to a dark photon that then decays to dark matter, and then the dark matter goes through some distance, right, like 0.5 kilometer, and then it goes into your neutrino detector. You look for dark matter scatter off some nuclei, right, in your neutrino detector. And this neutrino detector, right, is liquid argon. It's sensitive to low energy scatters. And so you can look for dark photons as well. And Mini Boon very recently did a nice, came out with this very nice result. So again, the y-axis is this y variable that everybody likes to use. The x-axis here is the dark matter mass, right? We're making the dark matter mass, the mediator mass 3 times the dark matter mass, and using this dark coupling of 0.5. Here's your relic line that appears in every plot. and here's the bound from the neutrino, from mini boom. So that's your bound, and you can see right here's the bar monophoton. So all of these kind of gray experiments, it turns out like this is one of the gray ones now, right? It's actually the most sensitive in this region around 100 MeV for dark photons.
Hi, how do you detect your dark matter in all these like detectors? Because I mean, for neutrinos, you look for CQE or CM.
So it looks like a neutral current neutrino interaction.
Then how do you differentiate this from your usual neutrino?
Yeah.
Yeah.
So
CQE, yeah.
yeah, so there's one big difference between dark matter and a neutrino. Do you have any guess? No. So I'll give you. I can tell you, right. The dark matter. Actually, here I'll give you a huge hint. Look at this axis. So the dark matter is heavy. So that means that its gamma is going to be completely different to the neutrinos, which means that if you can get the time of your beam coming in and you can measure the time of your interaction, the neutrinos are going to come in earlier than the dark matter. So you actually put a time window. Yeah.
Yeah, question about the plot on the next slide. Is there some kind of enhancement or resonance at, I can't tell what that is, but that little
Yeah.
point? Yeah.
2 times the muon mass.
Oh, okay, gotcha.
Yeah.
That makes sense.
I think, or no, it's 2 times the pion mass. No, so, yeah, it's 2 times. It's either 2 times the muon or pion mass. I think it's the pion. No, it's the muon. It's the muon. For sure it's the muon. Yes.
Okay.
Yes.
Thanks.
Okay. All right. So keep going. So one thing to say is that the detectors have to be very large here, right? Because this interaction is very weak, as is this interaction. So people like to say these experiments are suppressed by epsilon to the 4th, whereas other experiments are suppressed by epsilon squared. Okay, but the nice thing is that there's a rich neutrino program in the world, and so we'll be able to parasitically do dark photon and dark matter searches with these experiments. Here's another one that uses a super intense beam. This one is at Oak Ridge, so there's a spallation neutron source, and so it makes a huge amount of neutrons, which they use to study radioactive materials amongst many other things. But you can actually use this really intense beam. I think this might be the most intense proton beam. I think the only other one that might be as intense is the one in Sweden, the other spallation neutron source. And so you can imagine this beam is so intense that they use this to look for neutral current neutrino interactions. But you can also look for dark matter in the same way. So this is called, the experiment is called coherent. So they look for coherent. They look for neutral current neutrino interactions, 7s, right? And then you can imagine doing the same, looking for dark matter scatter off of some nuclei. So measuring. Okay. All right. So now we can also go and probe the lifetime frontier in other ways by just looking for long-lived decays of dark photons. And there are a few experiments that do this. And in fact, kind of the experiments that first started to do this were in the 80s. So, and here's kind of the first one, or the one that everybody likes. They made a super intense electron beam. This is in SLAC. And then they fired this beam into a hill. And then they put an experiment on the other side of the hill. And they just looked for dielectrons, right? So the idea is that you produce a dark photon, your dark photon lives for a few hundred meters, and then the dark photon decays and you look for 2 electrons. Yeah?
Thanks. Wouldn't there be some kind of massive background of electron interactions with stuff in the hill?
Yeah, it would all happen here.
Okay.
So yeah, all of the backgrounds basically die about 1 meter in. So maybe 2, right? So So you don't have to worry about backgrounds. The rest is just dirt that's blocking everything. So,
Gotcha.
yeah, dirt is really useful. So the other thing though is that depending on the size of your hill, you can only probe certain lifetimes, right? So in this case, we're probing lifetimes that are on the order of, let's say, tens of meters, right? And a kind of a good question for you guys is, what is the minimum and maximum lifetime that we can have? Well, the minimum lifetime, I think I showed in this plot, right? We can basically go all the way prompt, right? So we can have lifetimes that are on the order of microns. But the maximum lifetime, I don't know if you guys have any idea what this is. Do you know where the bound is for C tau? It's in the slide. You can go to the moon. So see, the maximum lifetime is on the order of the distance from here to the moon, assuming you're moving at the speed of light. And that comes from BBM. So the relative composition of the atoms in the universe will change if the lifetime gets longer than that. So that's always something to keep in mind. So here's this experiment. Yeah.
Just on that lifetime, is that only for thermal relic dark matter?
That's correct.
Okay, thanks.
Yeah, so so this experiment actually was done in the 80s by these guys. And so they actually used a ridiculous amount of electrons, but it actually remains to be the strongest bounds. So when we look at these dark photon plots where you see either the mediator mass or the dark photon mass, you see these bounds jutting out on the side. So these kind of triangle bounds are all long-lived particle bounds, right? With the longest lived ones being this E137, which is a SLAC experiment. Here's another long-lived particle bound. This is being run in Germany right now. So this is the Magix at Mesa detector. So Mesa, I think, is Mesa is the beam. Magix is the detector. And there are various detectors. So I think dark Mesa, which looks for long-lived ones. There's this Magix. There's this Mesa detector, which looks for shorter-lived. And it's a lower energy beam, so they probe low energy mediator masses, right? So at the tens of MeV range. And then here's another long-lived dark matter search. There's so many, like it just keeps going. There's this one's called the heavy photon search. This one is actually taking data right now. This is at Jefferson Lab. So they use an electron beam, and the idea is electron beam on a target. And then you have shielding that's on the order of tens of meters, right? They actually fire through some dirt. And then they have a detector on the other side that looks for dielectrons. And the idea here is to look for a specific lifetime. And so they actually get bounds kind of in a very specific region of the mediator mass and the coupling. Because this, if you remember, there's this lifetime varies. So they're only sensitive to lifetimes in this region, which is of the order of I think, like a meter in C tau. So of that order, you have to factor, it's whatever the lifetime is, but then it's boosted. So the actual length will be longer. Okay. So here's another one. Oh, this is the NA60. This is NA62. So here's an experiment I already showed you that looks for kaons. So it turns out that you can change the beam here. So you can, instead of firing, making a kaon beam and looking for rare kaon decays, you can also just fire a proton beam into the NA62 experiment, and you can look for long-lived dark photons. And so they can make actually bounds, and they can probe this mediator mass epsilon region. It can probe a little bit further than others. Here's my favorite one, which is called SpinQuest. So SpinQuest is an experiment at Fermilab. And the idea here is to fire protons. So like NA62, you have a proton beam. It has a 120 GeV proton beam. You fire it on a target, and you have a very compact target here with a magnetic field. And then on the other end, you have a bunch of muon chambers. And so in this case, you look for a dark photon to muons. But we're looking to instrument this guy with electromagnetic calorimeter. And then you can look for a dark photon that goes to electrons. And we call this experiment dark quest. So, and if you're interested in joining this experiment, please send me an email. So here are the bounds for dark quest. The bounds for NE62 are this purple line, so it's quite similar. And so here are the dark quest bounds. They probe a slightly different region. So it's actually smaller lifetimes. The beam is of similar intensity. There are other experiments here that you can ask about, like this phaser experiment and SHIP. Yeah, you can just ask me about them. I'll talk about phaser in a little bit. So finally, we can go to the LHC and look for long-lived particles as well. And so there's a long-lived particle detector that people are talking about building, and they want to build it near CMS. And so the idea is to build it on top, on the surface above CMS. And the idea is to make this detector as big as possible. And so kind of the model they're thinking to build this is IKEA. So the idea is to build an IKEA warehouse kind of structure, and then instrument it with cheap detectors, right? Large cheap detectors. And the idea is to look for particles, long-lived particles that are produced at the LHC, at the collisions, but then, live for a while and then decay in this warehouse of a detector. And there, yeah.
So I guess like missing ET bounds that CMS is putting on these searches would be extremely compatible with what's going on up there.
That's right. I'll get to that in a few minutes.
Okay.
And then there's one more. I'm trying to go through all of them so you know what the names are. Because if you go to a dark matter meeting these days, there's like a talk from every one of these experiments. And I might have missed one or two. There's a lot of them. There's another experiment called phaser, which probably, I guess Jonathan Fung gave a talk here, so he probably mentioned this. And the idea here is to have dark matter. It turns out that along the LHC collision axis, you just produce a lot of things, right? Most collisions are peripheral. So if you want to get as many sensitivity to as many collisions, low energy collisions as possible, you just instrument along the beamline. And there's this experiment that's being built right now called phaser, which is very close to the beam axis. And again, the idea is to look for a long-lived particle. So you imagine you produce particles here at the collision, they're long-lived, and then they decay. And you put some detectors, some eCal and some tracking detectors and so on. So that's another experiment that looks for long-lived. We can plot all of these. Oh, and finally, to bring it back to home, we can have the dark photon just be produced at the LHC in a normal detector without building a new detector. And this is actually, people are looking for this at LHCb. And this gives you a displaced dark photon. So if the lifetime is not so long, you can produce a dark photon and it will be displaced. Actually, sorry, this dark photon will be displaced. So these muon decays will be displaced from wherever it was produced, right? Say in a meson decay. And in fact, the displaced search is already been done once at LHCb, and these blue dots are the displaced search. The future displaced bounds will give you this box, right? And again, this is the mediator epsilon squared plot.
Is LHCb useful just from the lower luminosity, or?
Yeah, that's actually a great question. So LHCb, so for everybody, LHCb runs at a lower beam intensity than CMS and Atlas. It's about 1/10. So they get about 1/10 the data. And the question is, why is LHCb still useful when the big experiments are running with much more data? So the answer is actually that it's very hard to trigger these, right? And so in the big experiments, these displaced dimuons at the moment are getting thrown out. There's a lot of work at the moment, really a lot of work, trying to embed these kinds of ideas into the trigger system. And so I think these these LHC bounds will not necessarily remain the most sensitive in the future.
So they hope to, there's too many muons coming out at LS and CMS that your trigger is not competitive. Okay.
Yeah, it's the reason is these are low energy muons, right? They're like a few GeV. And you have a huge amount of muons just from like D meson decays, D meson decays. So it's kind of, there's a lot going on down there. All right, and yeah, I'll skip this slide. We can look at the bounds for these dark photons. So I showed you the LHC bounds. The Methuselah bounds actually are not so great. They kind of probe regions that people have already probed, right, with just these low energy electron beams. The bounds for phasor are a little bit worse than the Na62 and spin class 6 runs. So, and here's all of the bounds. And now this normally I've been showing the plot like this, but I found this recent paper where they went all the way down to very small couplings, to kind of the point where you get cosmological constraints, and you can see all these different bounds. I won't go into it basically because I think I went through almost all of these lines already, but you can stare at this and look at the different experiments. Okay. So kind of putting it all together, right? These are the bounds for visible searches. The bounds for the invisible searches are kind of driven by two experiments, Na64 and LDMX, right? And there's also these missing mass experiments. They're not as sensitive generally. All right, so here's a discussion question, and let's discuss this tomorrow. How do we find something that explains G-2 and dark matter? So now I want to talk about, kind of the next 10 years, what's going to happen. So in the next 10 years with direct detection, there's kind of a clear plan. They want to add more and more, make larger and larger direct detection detectors until they hit the neutrino wall. So eventually get to this Darwin experiment. And there's also, you'll hear talks about this, I'm sure, of experiments to get to the neutrino wall on the low mass side. With indirect detection, there's a clear plan to kind of build larger, either take more data with Fermilab, or to just build a larger high energy photon detector so that you can cross this Rayleigh line in the next 10 years. And then with the low mass, there's an attempt to kind of do the same idea now, right? To build experiments to cross these Rayleigh lines. So here's the Na64 bounds. And this, but then, once we start thinking about this, there's a number of different caveats, right? This would be for invisible searches. With visible searches, the Rayleigh line is not well defined, right? You can make one when the dark matter mass is less than the mediator mass, but heavier than the mediator mass over 2. But when the dark matter mass is greater than the mediator mass, well, you just have to believe that somehow dark matter is being produced. And here's the LHC bound for Higgs invisible. And so we can also take our monojet analysis and run this all the way to the full luminosity, and we can get a bound. And it's about 1% Higgs invisible. And then you can think about future experiments and take a 100 TeV machine, and you can run the same dark matter analyses at 100 TeV, and we can use the same scheme of simultaneous bits. The nice thing is that because we do this, there's no kind of systematics wall. So you can, as long as you can preserve this level of precision, so assuming you know how to be very precise, you can continue to just run this analysis as you take more and more data. So we can do projections with the future experiment. And this is for Higgs to invisible. And so the LHC we're able to get to 1%, right? With the 100 TeV machine, we can get to 10 to the -4, right? And just to show you what this means in terms of direct detection, yes, so there's no systematics wall. To show you what this means for direct detection, here's the current Higgs invisible bound compared to direct detection. So they're of similar sensitivity in the like dark matter mass of 20 GeV region. So the bounds kind of look complementary. And here's the future bound for Higgs invisible if you had a 100 TeV machine. So you can go well beyond the neutrino wall. Yeah.
It's 100. Thanks.
Is the 100 TeV machine, is that like plausible in terms of funding? Is there one being planned?
So CERN has declared that this is their project for the future.
Okay,
It's not necessarily guaranteed, but they're very actively thinking about this.
is there anything that like they think they should definitely be able to see, like the Higgs for the LHC?
Yeah, so I mean, I did this analysis, right? Kind of to show that you can do a lot of useful things. And so you can do like Higgs invisible well beyond any other experiment, right? Like deep into the neutrino wall, right? So you can write down a list of your favorite analyses and look at it. And typically the 100 TeV machine kind of destroys every other analysis at high energy, right? At low energy, there's a lot of interesting things you can do. But at high energy, I mean, if I were to pick an experiment above 10 GeV, I would pick a 100 TeV machine, right? I wouldn't even pick any plus or minus machine. But that's a subjective statement. Okay. All right, and yeah, so here's also the 100 TeV machine for kind of conventional dark matter. And kind of the fun thing is that you can actually, there is an upper bound to dark matter in the TeV region, right? So it's basically very hard to make a dark matter model with a TeV mediator beyond about 10 TeV. And if you make a 100 TeV machine, you can kind of definitively build this. So that's the other kind of motivation for dark matter at 100 TeV. But yeah, I want to now ask kind of the question of, can we make dark matter even more complicated, and does it help us out? So, you know, I kind of flashed through this Higgs invisible bound, but the idea would be that, well, with the current kind of conventional tools, we get this kind of sensitivity for Higgs to invisible. Without going through this plot, suffice it to say we can get to a branching ratio of 1%. With the full data. So how can we get below 1% at the LHC? Well, the idea is to make dark matter more complicated. And so far, I really haven't done anything with the dark matter. The past 4 talks, or 3 and a lot talks, have been all with the instance that dark matter is just some stable particle that decays from a mediator that interacts. But we can start to now ask questions, what if the dark matter is more complicated? So what, for example, if this mediator doesn't decay to dark matter, but decays to something that's unstable, that then decays to dark matter, right? And so now you can add now you've added some level of complication to your dark matter, but you get a lot of freedom because now you can look for an unstable dark matter decay that then decays to dark matter. So you get a new decay. And if you're lucky, this unstable dark matter decays to visible standard model objects and dark matter. So what does this give you? This gives you, well, instead of 2 particles, a new portal mediator and dark matter, you got a third particle that gives you a displaced object, right? So this unstable dark matter can give you a displaced object. And what we can do is, without any loss in generality, we can change our Lagrangians by adding these unstable particles. We can use the same class of mediators, right? Vector, scalar, pseudoscalar, whatever. But now we can just say it decays to unstable dark matter. It then decays. And this actually, yeah. And this is, you know, kind of in line with all the other dark sector ideas, is that, you know, we don't just have necessarily a dark matter particle in the dark sector. We can have dark everything, right? And so you can imagine, you can ask yourself the question if there's a dark Lazouche going on. Oh, I'm going to skip this. You guys probably learned about Friesen at one point. Suffice it to say, I get very depressed when I learn this. I'm going to just skip it. It's another way to motivate long lived, but We can talk about that in the discussion session. All right, so what's the simplest model that we can do where dark matter is unstable? So kind of a classic one is this inelastic dark matter. And so the dark matter is now unstable, it decays, and you get some displaced object. So now what we can do is go through the exercise of how do we redo our analyses now that we have some unstable particle, right? So you can imagine then taking like the monojet analysis, and instead of doing a met plus jet, you can do displaced object plus jet. And you can use all of the same toolkit that you used for monojet, but now you added displaced object. And you can ask all the same questions that we asked before, right? How do you build an inelastic dark matter model where you just make you make the decays unstable? So you can have the mediator decay to, you have the same mediators you want and it decays to something unstable. And what are the current model restrictions? Well, it turns out that if you run the relic, if you calculate the relic density, you get the same constraints that you got before for coupling to standard model, the same constraints for coupling to dark matter. The only thing now is you have an additional free parameter, which is a lifetime, and you can vary this lifetime as much as you want within the constraints of Big Bang nucleosynthesis and prompt, right? So you have complete freedom here. So let's use our knowledge of the LHC. Sorry. Oh, I'll just mention this, but I'm not going to talk about it. I'm going to look at the LHC, but you can do this with the beam dump experiment as well, where you can have a beam and make a long-lived particle. So you can have a dark photon decay to an unstable particle, and then this unstable particle then decays. Right, so you can do this with a beam dump, but you can also do this with the LHC. And so the way I'm going to do this is just take the monojet, and I'm going to give it some displaced object. So we have a mediator, decays to something unstable. These decay to displaced objects, and then we get a jet. So this is just a monojet analysis, but perturbed by adding displaced objects. And so what we can do then is we do monojet, we look for a jet, and we look for a displaced object. This displaced object can be, if it's in close to the collision, right, you can get a displaced vertex in the tracking detectors. If it's far from the collision, right, you can get a displaced object in something else, like a calorimeter. If it's really far from the collision, like it decides to go to IKEA or Methuselah, you can get something outside of the detector. And in fact, the nice thing about this is that in that instance, right, your signature inside the detector is missing energy. So you can imagine a monojet analysis, right? So you have missing energy. You can have a recoiling jet. So at the LHC, you know this is a monojet. And if you have something in Methuselah, right, you now have a displaced decay that you can correlate with the monojet. Yeah.
So if the decay length of this unstable dark matter is GM star, if it's short enough, then all of our analyses that we went over previously, are those essentially the same?
Yeah, so you can do everything is, so the nice thing is you can actually, once you identify the displaced vertex, as long as you can identify, you can remove it from the event, right? And then it's just a monojet analysis.
Mm-hmm.
The nice thing is that the displaced vertex, there's not a lot of displaced standard model objects. So you can actually reduce your background by a factor of 1,000, which is what I'll show in a second.
And I guess this inelastic dark matter, it's totally evades direct detection.
That's right. I think there are clever ways to get it in direct detection, but it's not, everything is heavily suppressed.
Mm-hmm.
Yeah, so what can you do with a displaced vertex? Well, you can take the monojet analysis and you can add a displaced vertex identifier. Atlas actually did a very nice analysis a few years ago with this. And they modified their vertex reconstruction. And so they can actually, if they have a displaced vertex that's like, this is millimeters, so like centimeters away from the collision, they have a pretty high efficiency for reconstructing it. So you can get with 80% efficiency a displaced vertex. And then what you can do is, so I did this exercise when I was trying to understand how interesting non-loop particles are, of just taking this analysis and running it on top of the monojet. And just as a note, what are the displaced objects you worry about? They're not typically not long-lived particles like hands and pipe. You have to actually worry about nuclear interactions. So this is I'll skip this. It's a very experimental thing to care about. You can ask me about this. But suffice it to say, you can actually reduce your background by about 10 to the, actually 10,000 if you have a displaced vertex ID. So you can take, if you want to just do a projection, you can take the monojet analysis, multiply it by 1 over 10,000. And then you can take a signal and you can convolve it with the vertex efficiency plots that you have from Atlas. And then you can do a bounds. And just to compare with something else, I also put Methuselah here. So we can compare a displaced ID inside the detector with a displaced ID at Methuselah. And yeah.
By displaced ID, do you just mean like a definitive tag on that interaction?
Yeah, so Methuselah, yeah, exactly. So just a displaced. So in this case, inside the detector, we look for a displaced vertex. In Methuselah, we just look for a displaced tag. There's like, again, it's a displaced vertex, but it's, you basically, the tag is very simple. It's just like a bunch of bits.
Okay.
So it's not, there's almost no background up here. So it's very easy to make a displaced object ID up here. Okay. Oh, I just wanted to mention, because I forgot to mention this anywhere else, is that there's another experiment called Codex B that's being proposed. That's kind of a competition to Methuselah. And it's like a little IKEA. It's a Lego IKEA. It's actually, here's LHCb and here's Codex B. So it's much closer to the collision axis, and so it's a lot smaller.
Yeah, so for all these displaced vertices searches, right? Your displaced vertex is like rare. So okay, but how do you correlate to the original guy? How do you know which collision or event it came from?
Yeah, so this is exactly the answer to this question is exactly the answer to the question you asked me before. The trick is to time this with this. So you measure the time of your displaced vertex. You know that things are moving at roughly the speed of light. The collision time you actually know very precisely. And so what you can do is you calculate the collision time, you multiply the collision time by the distance times the speed of light, and you look for a decay here, and you make a very narrow time window to look for your decay. So the timing is actually very important. And the other reason is that you get cosmic rays, right? Lots of them. And so you want to actually time this in very well. The other thing is you have direction, right? You have directional information from the particles. So for example, in normal detectors, you always worry about, or normal cosmic detectors, like neutrino detectors, you worry about downward going and upward going. You have the same downward going, upward going IDs in the system. So you look for upward going particles, right, that are timed in with the collision. Yeah, so are you satisfied?
As in I have no idea, because I mean, I'm not from collider things. So I just imagine that you have a mass of things at your collision site. So I'm just like, oh, okay, I guess you're timing that well to peg it back to one single event.
Yeah.
Yeah, okay.
So it's the, if you're familiar with beam neutrino, off-axis neutrino detectors, it's the same idea. Like T2K, they time it in with the beam profile, right? And like Minos, right, or potential or Dune, right? It's all timed in. You can calculate, the distance very well, right, from the beam, and so you can calculate the amount of time it takes to go from the beam to your detector. And you can time in your events. And this allows you to dramatically reduce the rate of background. Right?
Okay.
So it's the same, it's the whole idea is the same as with neutrino detectors. Right. I mean, the timing is difficult, right? We all know the opera, right? All right, so here's the LHCb. Codex B, this is another detector, just wanted to mention. Okay, so now what we can do is we can take a model. I'm gonna take a model of Higgs 2 invisible, which is kind of a standard benchmark these days. And then we'll make this Higgs 2 invisible unstable and decay. And you can make a plot like this, which is the number of events you would get as a function of your lifetime. So you can guess a lifetime, right? Which can be anywhere from a meter or centimeters to a meter. And then you can just calculate the number of events inside your detector volume. So the blue is inside the CMS or Atlas hypothetical tracker volume. The red is inside a Methuselah detector. These line up just, it's coincidental. But then when you correct for kind of acceptance issues, you get a plot like this. So this is a sensitivity corrected plot. So the y-axis here is the number of effective events, right? And so this is for the inside Atlas or CMS. This is the number of effective events inside an experiment like Methuselah. Codex B is quite similar. This is for specific branching ratio of Higgs 2 invisible of 10 to the minus 3. And so then what you can do is you can take these and make bounds. Here's kind of the nice plot of these bounds. So the kind of upper bound is Higgs 2 invisible, right? So at some point, right, you won't have enough displaced vertex events to identify these decays. So you just do Higgs invisible. So you want to be more sensitive than that. So this is the Higgs 2 invisible bound. And these dashed lines are if it's in the side Atlas or CMS. These solid lines are if it's in a big volume detector like Methuselah. And so you can probe lifetimes that are on the order of meters, right? At Higgs 2 invisible branching ratios that are on the order of 10 to the minus 4. And just to show you, this is a projection. To show you something real, these are the most recent results as of like a week ago. And so you can see this is Higgs 2 invisible branching ratio versus lifetime. The lifetime is in millimeters. So a meter is here. And suffice it to say that for these analyses, we can get to branching ratios of 10 to the minus 4. The left is for light particles. The right is for heavy particles. And you can see for light, right, we can get to these very small branching ratios. And for even heavier, we can get even better. Actually, we can go even further than those projections.
What's the cutoff between light and heavy here?
It's just based on these plots. It's the heavy ones here are close to the Higgs mass over 2. It's like 55. These ones are like 10. I would just read the labels. There's no like specific reason for this.
Okay.
Yeah.
Are you getting to, I mean, on this right plot, I see you getting to like, I don't know, 100 meters, almost a kilometer, and that seems very far for
So,
CMS.
so lifetime, right, is right e to the minus, right? So if you just look at your number of events, right, as a function of your distance, right? Even if let's say this is a kilometer, you're gonna get a lot of events right here. So it's just coming from the exponential.
And I guess it looks like the towels have the farthest length, and that's using the neutron detector as a towel.
Yeah. So this analysis, the one that X to tau tau, that's using the muon detectors and looking for displaced objects in the muon detectors. Yeah.
And I guess I'm wondering why the pink dye muon isn't towards longer distances. I would think that it could go farther.
So this is all right. Now we're asking real questions. These are kind of technical. So this is a scouting analysis. So scouting is the CMS word for trigger level analysis. So this analysis is done during the triggering process. And so long-lived muon identification is not in the trigger at the moment. And so we can only go so far. Okay. All right, so why don't I, let me just explain these. So I'll explain the projections now, and then we can stop. I had like conclusions, but I can do this tomorrow. So, and I actually have a few more small things. So here's the bounds if we just take projections to the full data set of the LHC. And this is now assuming an inelastic dark matter, but we do the same vector mediator model that we did before. And so what we can do is we can make this coupling bound, and this is the minimum coupling to get the relic density. And then we can project all of the analyses we want, right? So here's our coupling bound. And what we can do is then project future analyses. So the right here, this would be your heavy dijet analysis, right? So you can see you can get below this coupling bound all the way up to a TeV in dark matter mass. And then you have other, this is the boosted dijet, it's not as sensitive. The black is the monojet analysis projected out to the full data set. And then you can also take these other bounds. So the red here is the Methuselah experiment. And so you can see you can get down to coupling of 10 to the -4, right? So well below your minimum coupling line, and down to masses that are on the order of 10 GeV for dark matter. And if you just take this TK is the bound of a displaced vertex analysis. So if you just take the displaced vertex projections, you can get down to the kind of GeV level where you're below the coupling. And the important thing is that going from monojet to displaced vertex, it's an order of magnitude in coupling. Okay, so those are the bounds. We can do this for all of the mediators we want. Here's the axial vector bounds. They're basically the same. Here's scalar and pseudoscalar bounds, right? So varying the dark matter mass. Here's your relic line. It's very large in coupling. And you can see here's the black line is the monojet analysis. Now, if we have a displaced particle, we can reduce the sensitivity by an order of magnitude. And here's the pseudoscalar. And interestingly enough, the Methuselah experiment is more sensitive when the dark matter is light. When the dark matter is heavy, both the Methuselah and the LHC detectors are of similar sensitivity. And just to show you, right, these bounds are assuming 10 to the -4 with the full LHC data set. We've already gone to this point with the current LHC data set, so these bounds might be even stronger. There's a lot of room for being creative here. I'll skip this. This is if you had Susie. I haven't talked about Susie in this whole talk. All right, so there's a few more long-lived models I'd like to talk about, but I think I'll leave that to the discussion session. Thank you.
So before you go, just a reminder, the next session starts at 3:30. There's nothing right now, but the cookies are still there. Oh, one more thing. At 5, we're going to take another photo. So 5 p.m. During the break.